In this lesson, we are going to talk about the probability of compound events. So basically, and or probabilities. If you take a look, the word or in probability means to add and then take out the overlap. So when we look at mutually exclusive versus inclusive, when something's mutually exclusive, that means it can't occur at the same time. There's no overlap. Kind of like you can't be a boy and a girl. That'd be a good idea for that. But you can be a sister and a wife at the same time. So that's something that could overlap. You can have both of those roles. You can be a father and a son at the same time. But there are certain things that you can't have happen at the same time. So that's when it's an or probability and it's mutually exclusive. Inclusive means there is an overlap. For example, you can be a sister and a wife at the same time. And so the probability of that is you would add the two probabilities together and take out their overlap. And so you don't want to count the people who are sisters and wives twice when you count them as sisters and then as wives. And we'll kind of go through that as we do them. So from a deck of cards, remember we did the deck of cards before, so it says choose one card, find the probability you choose an ace or a king. Because there aren't any aces that are kings, these would be examples of mutually exclusive. But to start, I'm going to say, okay, how many aces do I have to choose from? So I have 4 out of 52 cards that are aces. I'm going to add the number of kings I can choose. So again, there are 4 kings out of 52 cards. How many cards can be a king and an ace? That can't happen. So my overlap that I'm taking out doesn't exist. There is no overlap. So we could say 0. We could skip that step, or we could say 0 out of 52, however you prefer to write it. So when I calculate the probability of an ace or a king, I add those up and I get 8 out of 52. So the probability of an ace or a king, picking that from a deck of cards, would be 2/13. So we do the same thing for the probability of an ace or a spade. So the probability of an ace we already talked about, that's 4 out of 52. The probability of me picking a spade, remember there's 13 cards in each suit, so that'd be 13 out of 52. And then how many aces are spades? Well, there's one ace that's a spade in a deck of cards. So I take out that overlap because that ace of spades just got counted twice. It got counted in this group and it got counted in this group. So I need to take out that overlap. And when I add those up, I get 16 out of 52. Or when I reduce that, I get 4/13. So that's the probability in a deck of cards I would pull out an ace or a spade, choosing one card. Probability of a club or a face card. So clubs again are a suit, so there's 13 clubs in a deck of cards. Face cards, if you remember, are the jack, queen, king. So there's 3 face cards per suit, which means there's 12 face cards in a deck of cards. How many face cards are clubs? Well, the jack of clubs, the queen of clubs, and the king of clubs. So there are 3 that got counted twice. So I take out that overlap. When I add those up, I get 22 out of 52, or when you reduce, 11/26. And then the last one, the probability that we have a red or a face card. So red cards are half the deck, right? That's 26 out of 52. My face cards we just talked about, that's 12 out of 52. Now, how many face cards are red? Well, there's 3 face cards per suit, remember the jack, queen, and king, and I have 2 red suits, the hearts and the diamonds. So that means I have the jack, queen, and king of diamonds and the jack, queen, and king of hearts. So there'd be 6 total face cards that are red. So that's my overlap. When I subtract that, I get 32 out of 52, or 8/13. Another problem where we're going to deal with ors, it's that a student is selected at random from a group of 12 male and 12 female students. There are 3 male students and 3 female students from each of the 9th, 10th, 11th, and 12th grades. Find each probability. So we have 3 male 9th graders, 3 female 9th graders, 3 male 10th graders, 3 female 10th graders, 3 male 11th graders, 3 female 11th graders, 3 male 12th graders, 3 female 12th graders. So there's what we have divided up. It says find the probability. So we're choosing from random a group of 12 male and female students. So total there's 24 students here, right? Let's just write that down. We have 12 males, 12 females. So it says, what's the probability I choose a 9th or a 12th grader? Well, of my 9th graders, if you take a look at the 9th graders, I have 3 males and 3 females. So of those 24 students, 6 of them are 9th graders. And then seniors, I'd also have 6 seniors, right? Are there any people that are seniors and 9th graders? No. There's no one that could be a senior and a 9th grader. So my overlap is 0. Or you could choose not to write it, that would be okay. So my probability of choosing a 12th grader or a 9th grader is 12 out of 24, or 1/2, which makes sense if you think about how they were divided equally. Now we have a 10th grader or a female. So I have 6 out of 24 10th graders. Wouldn't I have that for each grade, right? How many females do I have in this whole group? Well, I have 12, right? So I have 12 females in the whole group. How many of those females are 10th graders? So which ones are the overlaps? That'd be 3 out of 24. So when I add those up, I get 15 out of 24, or reduced 5/8. So now the last one here, male or not an 11th grader. So let's figure out how many males we have. We said that was 12 out of 24, right? Half the people are male. Not an 11th grader. So I know I have 6 11th graders, which means I would have 18, 9th, 10th, and 12th graders, right? Those would be not 11th graders, 6 for each grade. So that's 18 that are not 11th graders. And then how many males do I have that are not 11th graders? So since I have 3 males per grade, I have 3 in 9th, 3 in 10th, and 3 in 12th. So I have 9 males that are not 11th graders. When I add those up, I get 21 out of 24, or 7/8. So hopefully that makes sense for those ors. Whenever you have an or, you give the probability of both, and then if there's an overlap, you need to subtract that because that number got counted twice. Now we're going to look at some ands. And in probability means to multiply. So when you see an and, we multiply. Notice in your notes we have the line that says assume no replacement if it doesn't state otherwise. So we are assuming they don't replace something. That's what we always assume. So if they don't tell us, we assume no replacement. So number 3, it says from a deck of cards, find the probability of 2 kings with replacement. So 2 kings, it doesn't have the word and here, so you have to assume this means an and problem because it doesn't have the word or. So the probability of 2 kings, well, the probability of drawing 1 king is 4 out of 52, right? And since it's and, we multiply. Since it said with replacement, I'm going to take that king out of the hat, and then I'm going to put the king back in. So what's the chance I draw a king again? Same probability, 4 out of 52. When I multiply those two numbers and reduce that fraction, I get 1 out of 169. So when you draw 2 cards out of a hat, and you put them back, so the first one's a king, put that king back, mix it up again, draw another king, the chance is 1 out of 169. Now in the second one it says 2 kings without replacement. So on my first draw, my chance of drawing a king is still 4 out of 52. Then the king that I pull out, I keep that king and I don't put it back in. So I only have 51 cards in my hat. How many of those cards are kings? Well, since I pulled a king out already, there's 3 of them that are kings. So when I multiply those and reduce them, I get 1 out of 221. So hopefully that makes sense with and without replacement. Number 4, it says we have a cooler that contains 3 Mountain Dews, 4 cans of Pepsi, and 3 cans of Dr. Pepper. What's the probability I grab 2 cans of Pepsi without replacement? So let's add up here. We have 10 cans of pop total. So to get a can of Pepsi, since there are 4 of them, I have a 4 in 10 chance of getting a Pepsi when I grab it. Then I put the Pepsi back, mix the pops up. What's the chance I'd pull a Pepsi out again? 4 out of 10. So when you multiply those together, you get 4/25 when you reduce that fraction. So that's the probability of pulling out 2 cans of Pepsi with a replacement. Now without replacement, my probability for the first one is the same, it's 4 out of 10, but I keep that Pepsi and I go into the cooler and grab another can of pop. So now there's only 9 cans of pop in there, and of those 9 cans of pop, 3 are Pepsi, because I already pulled a Pepsi out. When I multiply and simplify that fraction, you should get 2/15. Then P says Pepsi, then Dr. Pepper, then Pepsi. Now they don't tell us about replacement here, so just like on the front it says assume no replacement. So we have to assume no replacement here because they didn't say anything, and that's our job. We assume no replacement when nothing's said. So in my first grab of Pepsi, I have a 4 in 10 chance of getting a Pepsi. I keep that Pepsi, so there are now only 9 pops left in the cooler. How many of them are a Dr. Pepper? 3 cans of Dr. Pepper, right? So I have 3 out of 9 cans of Dr. Pepper, so now I keep the Dr. Pepper. So in my hand right now I have a Pepsi and a Dr. Pepper. I reach back into the cooler where there are now 8 cans of pop. How many of them are a Pepsi? Well, there were 4, but I've taken one of those Pepsis out, so now that's a 3. Now when you multiply all those numbers across, you're going to see that you would have a 1 in 20 chance of grabbing a Pepsi, then a Dr. Pepper, and then another Pepsi. So now as we look at number 5, you can see there's a spinner here. It says a die is rolled and the spinner is spun. So this should be equally divided up here, where we see that we have the die with numbers 1 through 6, right? And then we have about a 1/4 chance for each of these. Even though this doesn't necessarily look exactly divided up, it is. So it says find the probability of a prime number, then yellow. So this is an AND problem. Probability of a prime number. So think of your die, you have the numbers 1 through 6. There's our 5, huh? So the prime numbers in 1 through 6, what are my prime numbers? 1 is a prime number, 2 is a prime number, 3 is a prime number, and 5 is a prime number. So I have 4 out of 6 that are prime numbers. So that'd be 4 out of 6. And then I'm going to multiply that by yellow. So what's my probability of getting a yellow when I spin this spinner right here? Since I only have 1 spot of yellow, that's 1/4. So as I multiply that across, I would get 1/6. Next, we see the probability of getting a number greater than 2 and then green. So greater than 2 would be the numbers 3 through 6. So again, we have 4 out of 6 chance there, times a green. Since we have 2 spots that are green, that's really half of our spinner. So I'd have 4 6 times 1/2, and when I reduce that fraction, I get a probability of 1/3. The last one we're going to talk about are coins that are tossed. And it says we toss a coin 3 times. Now remember, when you toss a coin, you always have replacement. So we could make a tree diagram here so we can kind of look at what we have, and I think that's a smart way to start. My first toss, I'm going to get a heads or a tails. My second toss, heads or tails, heads or tails. And then my third toss is heads or tails. Oops, let's make that a little closer. There we go. Or heads or tails. And then here I have heads or tails, and here I have heads or tails. So if you want to list your sample space, that might help you when you're trying to figure this out later. If you don't need to do this, you don't have to. It's only if this helps you so you can see how many total options you have. Like right now when I'm done, I see that I have 8 different things that can happen. So there's 8 possibilities here. So it says find the probability of 3 heads. Now there's a couple ways you could do this. You can look at what you just did and say, oh look, there's only 1 out of 8 ways that I could get 3 heads. And so you know the answer is 1/8. I also want to show you that you could do what we just learned about the ands. What's the probability you'd have heads on your first toss? 1/2. Second toss? 1/2. Third toss? 1/2. Which still equals 1/8. 3 tails you can look at. Again, 1/8. I think that one you don't even have to look at. You just know that would be the case. No heads. So the probability of no heads, take a look at your thing. Doesn't that just mean 3 tails? I don't think that one's too hard, right? 1/8. It's another way of saying 3 tails. 1 head. So take a look at my chart here. How many of these have just 1 head? Here's one. Here's another. Here's another. So I have 3 of them that have 1 head. So that's a 3/8 chance. The next one says head, tails, tails. Because it's worded that way, it has to be in that order. So head, tails, tails is this one right here. So there's only one chance of that, which would be 1 out of 8. And then the last one is at least one head. Well, we just figured out all tails is 1/8. So everything else would have at least one head. It could have 2 or 3, but that'd be 7/8. And you should get the same answer if you look at your sample space also. Hopefully that makes sense to you. You'll have an objective on this tomorrow and also a worksheet. But let me know if you have any questions.